Hello everyone. We're going to continue our math lecture series here. In the previous lecture I had proven that there are infinitely many primes. I had, however, not adequately described what infinity is, as some of the feedback I got has demonstrated. So we're going to talk about that here. So our topic today is what is infinity? And to get us started, we are going to just limber up with this little riddle here. So I'm thinking of some object, concept, or person or something like that, and it has the following properties. It's faster than light, darker than black, emptier than a void. So the question is, what is it? If you want, you can hit pause or yell out the answer or whatever. And if you've hit unpause now, you know that the answer is nothing. Right, it's just to limber up your mind so we can put our brains into gear. So the user GKLR responded to me in a video in which he suggested perhaps that infinity should not be so easily defined, because that's sort of the refuge of where the religious go, and that the question of whether or not there is a largest number is a philosophical one to him. Well, as a mathematician, that simply isn't good enough for me. If philosophers wish to take that position, then they are parting company with the mathematics. Infinity is a well-defined concept from mathematics, and the question about whether or not there is a largest number has a definitive answer, and that is that there isn't one. And that isn't a philosophical point of view, it's a necessary mathematical point of view. So when I talk about infinity, I'm talking about a well-defined concept of one in mathematics. And for other disciplines to try and borrow it and then just change the definition is, it's kind of an affront to mathematics, because mathematics as an entire field would collapse if there was no definition for infinity that was rigorous. I mean, seriously, just close your math departments in all the universities if you had no infinity. So, to get you thinking about it, I'm going to suggest the following simile here. Infinity is to numbers as atheism is to religion. So obviously atheism isn't a kind of religion, it's in fact, atheism is a property that people have that because they do not follow a religion, whereas religion is a specific indoctrination or a philosophical set of beliefs or something like that. So we can see that atheism is not really a religion, and in that same sense infinity is not a number really. It's just we're going to learn that it's a sort of property. So infinity is not a number. Let's start with that, just to clarify, and then we're going to have some definitions. A set is finite if it has a number of elements which is a natural number or 0. Okay, that's pretty straightforward. I mean, if you just have a set like 1, 2, 3 or something, well, that has 3 elements, and 3 is a natural number, so we're okay with that. So this leads us, of course, to the sort of atheist definition for cardinals or whatever you want to call it. a set is infinite, if it is not finite. So, of course, GKLR will object that I haven't demonstrated that there isn't even an example of one. So, but let me first just state that we can see here that infinite is, defined as sort of the complement of all things which are finite. Okay. Finite is basically any sort of ordinary tangible set of things. If you have a 0 objects, that would be like the empty set, or you have 10 objects of some kind, or 10 numbers, or whatever, or 1,000, or whatever, then that's pretty clear what a finite set is. And just infinite is anything that's sort of not any of that. And so let's okay. I'm going to give some examples, but before I do that, I'm going to put another property here. A set which is infinite is not necessarily let's just say it's not a set which contains the symbol infinity. Okay, so if we had this magical set which we thought was infinity, that doesn't mean it contains some magical element in it which is denoted by infinity. And to try and make that clear with an analogy, if I had a pail, one question we could, it would be comparable to saying a pail a pail carries green in it, right? Rather than containing rocks or something. The rocks of that are inside of a pail may be green, or the pail may be green, but it doesn't contain something green in a sense, right? So because infinity is an adjective, it's not a symbol or a thing that. It can be in some weird kinds of mathematics, but we're not going to really touch upon those. Those are all bootstrapped by ordinary mathematics anyways, in which we are ignoring such things because they don't make sense. So I'm going to give some examples now of, and hopefully these are fairly obvious. So for finite, we're going to just go ahead and say the empty set, sometimes denoted by that, or just some simple set, 1, 2, 3. Or in fact, you might imagine some set 1, 2, and then a million. So this is a set with 0 elements in it. So that's a 0 is a number or whatever. So that's what makes it finite. And this is an element with, of course, 3 elements in it. And so that's finite. And 1 through infinity, that's got an infinite number of elements. Or sorry, that has a million elements in it. So that is finite as well. So we're going to go ahead and do infinite now. So the natural numbers, which are 1, 2, 3, and sort of go off forever. So the set of all natural numbers is infinite because there's no largest element, and there's no you couldn't say exactly how many elements there are either. So, because for any finite number of elements you think are there, say a trillion or something, you just say, well, but if I count the numbers from 1 to a trillion plus 1, those numbers are all natural as well, so that couldn't be it. So this is an infinite set, but I want to give some other really good examples too. So if we take just the even numbers and I'm going to just call that n sub e, we see here that, well, we have the same problem, right? Like, there's no largest even number, because as soon as you present one to me, I can add 2 to it, and that would be another larger even number. So that one's infinity as well. And of course, odd. No surprises there. And of course, from the previous lecture I did, the set of prime numbers is also infinite. Okay? So these are fairly good examples. And so I want you to just pay attention to these 3 examples here. These, so the even numbers and the odd numbers are disjoint. They don't intersect at all, yet both are infinite. Furthermore, the set of all natural numbers is a proper superset of either of these 2. In fact, it's the exact disjoint sum of these 2. Yet all 3 of them are considered basically infinite, right? They're just given the same category of infinity. They're not actually distinguished in any real way, and maybe in a future lecture I can explain that to greater detail. They're all just classified as infinity. So, just want to put up another property here, though. For sets of integers, it is possible to have a lowest or highest element in that set, but not both. Okay? So this actually addresses a logical inconsistency by Darphius, who likes to commonly prove the non-existence of infinity as proof of God. I don't really follow his logic at all, but in any event. So we saw as examples of, like, the natural numbers is clearly an example in which we have a lowest element, namely 1. Right? But we might imagine the set of negative natural numbers. Negative 1, negative 2, negative 3. In that case, we would say negative 1 is actually the highest element rather than the lowest. Right? And these are both infinite sets, and you see that they have a boundary on one side. Okay? And if we were, say, to take the set of all integers, well, that sort of grows in 2 directions. I hope that comes out as readable. So that's not bounded on either side. There's no largest element or smallest element. And all these sets are infinity. Again, they're all under the same classification of just infinity. Okay? So what I've described to you, and I'm sorry if I butcher this, but I'm not a Hebrew writer or speaker or anything like that. So this is these are all examples of infinity that are denoted of aleph naught. So this is some symbol from Hebrew writing. I don't know if it's aleph naught. So, and I can, in future lectures, for example, I could explain the different alephs. However, these are just the kinds of infinities we get from unbounded integers and natural numbers. So I'm going to give another example here. Let's say that's a badly drawn racetrack, but whatever. So we have this car, and we imagine we're going to drive the car on this racetrack along this path. And this is just a circular racetrack, so it doesn't have any kind of end to it. You can just keep going and going and going. So a simple question we could have is, what is the longest path that this car could travel along this circular track? And of course, there is no longest path, because as soon as you've because it's a circular path, it means that there's nothing stopping you at any point. You can always just keep driving. So as soon as you come up with something that you think is a candidate for the largest length, you just drive a little bit further, and that would be even larger. So there is no largest path, right? So you might write the following: the longest path, just referring to this, is infinite. Okay, and so this is sort of where we can commonly get the delusion that infinite, or we come under the common mistake of thinking that infinite is a noun or is an actual number or something like that, because it seems the way this is worded says the longest path is infinite. So infinite is the quantity of what the longest path is, and it's like, no. In fact, this is an adjective. The only noun in this sentence is, in fact, path, right? So if we remember that infinity really means not finite, right? So the longest path is not finite, then it makes sense, right? It's really just an adjective. Okay, the other point of this example is that we have created a sort of infinity here, this longest path, inside of a finite context. Okay, because this racetrack is just a finite thing, and suddenly we have infinity showing up, embedded inside of it, right, as a concept, because infinity is a concept. It's not an actual object. So when people say infinity doesn't exist, you have to question, right, because infinity can't exist within a finite context. I mean, Darphius has said this in his previous videos, and it's like, no, that's utter nonsense. Infinity is an abstract concept, and of course it can exist within a finite context, and this is an example of such a thing. So this brings us to the end of this lecture on infinity. Obviously I'm looking for any feedback. I'm planning on doing a follow-up lecture on this to address Zeno's paradox, which is also under the topic of infinity. Thank you for listening.